Hi, welcome back to Chem with Chem. In this session, we're going to be working question 3 from Chemistry Paper 2 of the January 2019 sitting. If this is your first time to the channel, then please check out the other materials that are here. Like if you find value, share with a friend, and consider subscribing and turning on post notifications so you'll never miss out when new content is added. Let's get right into it. Just looking at this, we're seeing energy coming up, and what a time it is. Oh my word. Organic chemistry, it is. Compound A is a straight chain hydrocarbon with the molecular formula C5H12. Part 1. State one natural source of hydrocarbons and two possible uses of compound A. Now we're going to just list out all the natural sources. Over answering, if we get a question like this, you would just give one. But the natural sources are naturally natural gas. Well, it's not called naturally natural gas. Natural gas, crude oil. Crude oil is also called black gold for obvious reasons. Crude oil is another name for petroleum. And another source is biogas. And this compound here with the molecular formula C5H12, I think it's something we've seen already. That is pentane. That that is coming from the alkane series. Now, a use of pentane could be used as can be used as a fuel. It can also be used as an organic solvent, where it can be used to dissolve non-polar substances. So that would give us 3 marks. Part 2, draw the fully displayed structure of compound A. So the molecular formula is C5H12. This is a saturated hydrocarbon. So we'll draw our 5-carbon skeleton and we adorn them with the hydrogen. In a deja vu moment here, the more we practice, the more this thing just becomes second nature. Even drawing will be muscle memory. So here we go. Each carbon must be taking part in 4 bonds. So that's that. And 2 more marks. Part B. 1. Thermal and catalytic cracking are very useful processes in the petrochemical industry. Define the term catalytic cracking. So let's just get right into it. Don't want to use but the word cracking. We probably over answered part 1 a little bit by putting in more useful. It's the breaking up of long chain hydrocarbon compounds into smaller hydrocarbons using a catalyst or into shorter chains. And the importance of catalytic cracking in the petroleum refineries in part 2 here is that the smaller or the shorter chain hydrocarbon compounds are more useful. So we'll just state that smaller products or smaller chain or shorter chain hydrocarbon are more useful. So they burn more easily, right? So diesel doesn't burn as well as octane. So that the heavier the fuel or the longer the chains, the longer the fractions, the harder it is for them to burn. So they would not be very good accelerant. So kerosene burns easier than diesel, which still burns easier or more easily than heavy fuel oil, and so on. So that's it. 3 more marks. Part C. Another hydrocarbon, compound B, with the formula C5H10, can be converted to compound A in a simple one-step reaction. Part 1. Draw a possible fully displayed structural formula of compound B. C5H10. This is similar to the one we saw earlier. This is similar to compound A. Compound A we said was C5H12, and B is C5H10. And the difference here is just 2 hydrogens. And they're saying that B can be converted to A in a simple one-step reaction. Now, what would the fully displayed structural formula of compound B look like? Well, in order for us to get a compound with this formula, it means that there will have to be a carbon-carbon double bond. So in compound A, we said that this was saturated. Compound B is unsaturated. So we'll still have 5 carbons. So let's go, but somewhere in the mix, we're going to have to put on a carbon-carbon double bond. You could put it between carbon 1 and carbon 2, or between carbon 2 and carbon 3. So in this case, I'm putting it between carbon 2 and carbon 3. And you're probably saying, but how come? It's because I'm counting from the right-hand side. You can count from any side, right? So I want to ensure that each carbon is taking part in 4 bonds. And we'll put on our hydrogens. That's it. And they want us to, in part 2, state one physical property common to both compound A and compound B. All right, so physical property. So they would be both liquids. That's one. And we could also say, so a second one, they do not dissolve in water. And that would give us 3 more marks. How many marks have you gotten so far? At the end, please say how many you got out of the 15. Part D, last 4 marks. So we've gone 11 so far. Compound A and B can be distinguished by reacting them with bromine solution in the dark. Part 1. State which of the 2 compounds, A or B, reacts with bromine. So just a reminder, compound A is C5H12 and B is C5H10. All right, so A is an alkane. I mentioned that at the beginning. And B is an alkene. Now, the one that reacts with bromine solution in the dark, it would be the alkene, which is compound B. State the color change that is observed when the reaction occurs. That's part 2. Well, when we're given a color change, we have to state the former color and we have to change the final color. Former state, final state. So we don't even have to write this in a sentence. We'll just say brown to colorless. So alkenes will decolorize bromine water, but you have to state, or bromine solution, but you have to state the initial appearance of the bromine water or the bromine solution. And they want us in part 3 for the last 2 marks now to make it up to 15 to write a balanced chemical equation for the reaction. So I'm going to be consistent. I'm going to use the same formula, same displayed formula I used earlier on, where the carbon-carbon double bond was on carbon 2. So we're going to draw out everything so we can see what is happening. We'll need as much space as possible. So let's go. So this is compound or alkene. 1, 2, 3, 4, 5. So this would be pent-2-ene, or some books will say 2-pentene. But convention says pent-2-ene, but anyway, doesn't matter. So that's our compound B. And this now we would add, it's an alkene. So we know alkenes undergo addition reactions, and we would be adding across double bond. So let's use something different for the bromine. So this is Br2, and that's a liquid, and the condition we're going to be using there is CCl4 because it's bromine solution. So bromine would be in tetrachloromethane. Like dissolves like, tetrachloromethane is an organic solvent, which is nonpolar. So it would dissolve bromine, which is nonpolar, like dissolve, like dissolves like. So the final thing, we put space, but we're going to see if we can scrunch it up here. 1, 2, 2, 3, 4, 5. This should do. So right between, let's highlight it. So just keep looking right there. Goat. All right, so we're gonna zoom in on the same area in a little bit. So let's put on back the hydrogens. Okay, what did we do? Need back our pen. All right, hydrogen, 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 hydrogen. Okay, so let us switch our here. That's where we're focusing on. All right, so right where the carbon-carbon double bond was, we're just going to break one of them. And when that happens, it means that each of those carbon atoms that was, sharing the carbon-carbon double bond will now be able to take on a bond with the bromine. So we say we're adding bromine across the double bond. So since we had the bromine in black, we're going to put them on in black. So this is what we would have as the final product. And just like that, you got 2 more marks. Okay, please state in the comment how many marks you got out of the 15. And remember to like if you found value in this video, share with a friend so they can find value as well. And if you haven't subscribed, then just hit the subscribe button, smash the bell, as my little boy would say. So you'll never be left out, or you'll be notified when new content is added. So thank you for joining Chem with Kim, and see you in the next video.